Hi all, this is a video giving some examples of linear functions, particular finding equations and graphing linear functions when your information is given in function notation. So again, I am running on a little bit of an assumption that you are familiar and comfortable with finding equations for lines and graphing lines, and what's supposed to be new here is just having the information that you need given to you in a little bit different notation. So I have a handful, I think 5 examples here that I'll work through. So this might be a little bit of a longer one, but hopefully we'll get going and it won't take us too long. Okay, so first one, we're told that p of x is a linear function and we're given 2 pieces of information. 1, p of 0 is 7. 2, p of 3 is 5. So if you will remember, to find an equation for a line, there are certain combinations of information that will work for us. So one option is 2 points. If we're given 2 points, we can find the equation for a line. The other information would be point and the slope, and it can be any point. It's fabulous if we're given the y-intercept and the slope, because then slope-intercept form gives us the equation without having to do any extra calculations. But actually any point on the line and the slope of the line uniquely determine a linear equation. So our first job is to look at the information we're given and decide what it is. Are we being given 2 points? Are we being given slope information? What is it? In this case, p of 0 equals 7 and p of 3 equals 5 is all point information. So when I look at this, if you'd like to rewrite it, this is saying that p goes through the point 0, 7, and p goes through the point 3, 5. Again, the beauty of function notation is it not only tells you the ordered pair, but also which function pairs the two. But you can always translate back into a point if it's helpful. Okay, so given 2 points, we actually have to know the slope of a line in order to get its equation if we're using our slope-intercept form or point-slope form. But given 2 points, we can calculate the slope. So let's start with that. The slope of a line is change in y over change in x. So I'm going to do 7 minus 5 over 0 minus 3. Again, what's really key is that as soon as you choose 7 to be the first y value on the top, you have to use the corresponding x value first on the bottom. So it looks like we are getting a negative 2/3 for our slope. So we can actually start to write the equation for p of x. We'll put it over here. If we're using slope-intercept form, p of x equals mx plus b. We now know that the m is 2/3. Don't forget the x, it's important. You've got the variable in there. And then we're actually really lucky in this one. We're given the y-coordinate of the y-intercept. We were given the y-intercept, in fact, at 0, 7. So we know without doing any extra work, since p of 0 is 7, this should be negative 2/3 x plus 7. I didn't leave myself a ton of room, but I'll do a quick rough sketch. Again, this is just to make sure that you remember some of this stuff. Hopefully you already know how to sketch lines. We were given 2 points, so we can use that information. We know the line goes through 0, 7. Let's see, this is 1, 2, 3, 4, 5, 6, 7. And we also know that the line goes through the point 3, 5. 1, 2, 3, up 5. Oh, lost a parenthesis over here. And really that's enough to get us a pretty decent sketch. We can also use the slope. The slope is negative 2/3, which means if our x value increases by 3, our y value should increase by 2. And we can see that that's already happened once. We went over 3 and down 2. But we could repeat it again. We go over 3, which would give us an x-coordinate of 6, down 2, which would give us a y-coordinate of 3. Let's see if I got that about right. 6, 3. And we can continue to get as many points as we feel like we need. Really 2 points should determine your shape fairly well. If we go over to 9, we would be down to y equals 1. And it'll continue like this. Sort of a crookedy line. Okay. So there's our first example. I may not graph all of these, but I'll try and make sure I do a couple for the review. The next example is m of t is a linear function. We're given that m of 0 equals 2. So this again is a point. It's actually a really nice point. We're given the y-intercept, which is always handy. We can work with other points, but that one makes life easier. And then we're given what might look like some pretty mysterious information. M of 3 minus M of 1 is equal to 4. Okay, so again, I want you to keep in mind that what this packet is really all about is reviewing a little linear stuff and getting very comfortable with function notation. So this m of 3 minus m of 1 equals 4 is giving us very specific and useful information. We have to make sure we're clear on what that is. This is not telling me a point. It's not telling me that when I plug in 3 I get out 4, or that when I plug in 1 I get out 4. It's telling me if I plug in 3 and plug in 1 and then find the difference between the outputs, the difference is 4. So again, I want you to remember every time you see something like m of 3 or m of 1, this represents an output. So this is a y value minus a y value, otherwise known as rise. So this is just a recognition thing. When you see that statement, you should recognize that what you're really being told is that the rise for our function is 4. That's not quite enough to get slope. We would also need to know the run to get slope. But this again is the beauty of function notation. If I'm looking at m of 3 minus m of 1, yes, I'm thinking y value minus y value, but hidden in that statement, I know exactly which x values. So if I have x values of 3 and 1, I know that my run is 2. So to build my slope, I'm going to take rise over run, and I'm going to get that my slope is 2. Just to get into this a little more, because I know some people get stuck here, if you look back at your function notation version of slope, it says f of x2 minus f of x1 over x2 minus x1 is slope. So we can work on that in this problem. In order to get slope, we would need to take what we've been given, m of 3 minus m of 1, and divide it by 3 minus 1. We were told up above that the top, m of 3 minus m of 1 is 4. And we know that 3 minus 1 is 2. So here again is where I'm getting the fact that the slope of the equation is 2. This is enough to get me started. So I could say m of t is equal to 2t. Please pay attention to those variables. I know sometimes I will forget and use the wrong variables, but I want you to try and pay attention and use whatever variables you're given. So in this case, t, not x. And then we were lucky once again, we got the y-intercept for free. So the y-intercept is also 2. So there's our equation. I think I'm going to skip graphing on this one, but I'll snag another one when we get some messy slopes and make sure that everyone's clear on that. Okay, next one. H of y is a linear function. H of negative 2 is 0. H of 1 minus h of 0 is 1/3. Okay, so h of negative 2 equals 0. This is information about a point on the graph. It's not the y-intercept. Ooh, actually, it is the y-intercept, but here it's a funny variable as I define y to be my input variable. So y is actually on the horizontal axis. So this is not my b value. This is telling me about my horizontal intercept, not my vertical intercept. Okay, and we'll have h of y values up here. And then h of 1 minus h of 0 equals 1/3. Again, the whole idea here is to get used to what you're being given in function notation. So if I'm told that h of 1 minus h of 0 equals 1/3, I should immediately look at that h of 1 minus h of 0 and say that's the difference between two y values, two outputs. And again, in this one, our y values are actually horizontal. So this is the difference between two outputs, otherwise known as rise. So this statement is telling me that my rise is 1/3. If I want to build a slope out of this, I need to identify my run, but again, in function notation, that should be really easy. My x values are 1 and 0, which means the distance between them, or the run, is 1. So the slope is 1/3 over 1, or just plain old 1/3. Okay, now if I want to finish finding the equation for this thing, so far I've got h of y is equal to 1/3 y. Again, I know this probably bugs the heck out of you using y for my input variable, but it's totally legal to do that, and we want to make sure we're not too attached to y always being output and x always being input. Okay, and then we would like to have a plus b on there, but we weren't given the value of b for free. We were, however, given a point. So we can use that point in a couple of ways. One way is using point slope form. The other way is we can actually just stick with slope intercept form and solve for our b value. So let's see, on this one, I think I'll show you point slope form, but I will try to make sure in another example to show you how you could stick with just plain old slope intercept form and not have to switch back and forth. Okay, so what we know so far is that our slope is 1/3 and that the line goes through the point -2, 0. So according to point slope form, if we take h of y minus our specific y value, this is actually going to work out beautifully here, 0, that should equal to the slope multiplied by y minus our specific, again, confusing using y as our input variable, so our specific output, our specific input, because it's minus the -2, it will become a +2. This one's really easy. We don't even have to add anything over. We just get h of y equals 1/3 y plus 2/3. So I'll go ahead, since I started writing this over here, and fill it in. 1/3 y plus 2/3. Okay, let's go ahead and just work a little bit on graphing this one. I know when fractions are involved, people tend to have the most trouble. This is itty bitty, but I think we can actually get a little bit of a start just using this. So we know, based on the equation, that we have a y-intercept of 2/3. So let's say this is 1. Okay, so we're going to start at 2/3. We also know that our x-intercept is at -2, but I've just set up my axes, so I don't think that's going to fit very well. So we'll just use the slope to get other points. There's a couple of ways to look at the slope of 1/3. So right up here, we can actually see a couple of them. I could look at this and say my rise is 1 and my run is 3. So if I go over 3, I need to go up 1. I could also look at it this way and say, if my rise is 1/3, my run is 1. So I go over 1, up 1/3. And I actually think I like this one based on the little tiny scale I've given myself. So if I'm starting at the point 0, 2/3, and I'm using rise of 1/3 with a run of 1, I could say when I go over 1, I go up 1/3, which gives me a y value of 1. If I go over another 1, I go up another 1/3, which gives me a y value of 1 1/3, or 4/3. In general, if I can do it easily, I'll always switch to improper fractions because they're way easier to work with if you're going to do any sort of arithmetic after the fact. Okay, so there's the graph. So slope of 1/3 is going to give me a not very steep positive slope. So my function should be increasing. Y value should be getting bigger, but they're not doing it very quickly. Okay, 2 more. If k of x is a linear function and k of 0 equals 3, and k of x plus 1 minus k of x equals -1, find an equation for k. Okay, so this first piece of information hopefully is getting pretty familiar. That's a point, and once again, it's actually a very nice point. That's my y-intercept. So I have a b value right off the bat. B is equal to 3. This looks even more cryptic than before, but it's actually really similar information. This is just a little more general than last time. Instead of telling you what x coordinate to start at, this just says if you start at any old x value and increase your x value to x plus 1, then the difference between your y's will be -1. So this is still a rise statement. Even though I'm being a little more cryptic about which 2 x values I'm using, this is still saying y value minus y value. So again, anytime you see k of something, k of x plus 1, k of 7, k of -3, you're always referring to a y value. Y value minus y value is always a rise. So I'm being told that my rise is -1, and I need to identify my run, which in some ways is actually even easier here. So it might look a little more mysterious, but this is saying no matter where you start, this is your first x value, your second x value is always going to be 1 bigger. It's always going to be x plus 1, which means your run is always 1. So if we want to calculate a slope here, we would say rise over run is equal to -1. And we have complete information for an equation. So k of x is equal to -x plus 3. Slope of -1, you don't have to write the 1, it's implied. Y-intercept at 0, 3 means our b value is 3. Okay, last one. More of this kind of messy looking notation. If b is a linear function and b of 1 equals 4 and b of t plus 4 minus b of t equals 3, we want to find an equation. Okay, so once again, we're being given a point. We'll have to do a little more work this time because our point is not the y-intercept. We're also given partial slope information here. We have to piece it together a little bit. So whenever I see b of t plus 4, I'm thinking, okay, that's a y value for function b. B of t is another y value. So if I take the difference between two y values and get 3, that means that my rise is 3. With function notation, you can always see what your x values, or in this case your t values, are. So I'm starting at t and I'm stopping at t plus 4. So we should be able to see there that t plus 4 minus t is always going to be 4. So this is basically just saying it's a linear function. No matter what your starting value is, if you choose a fixed run, you will get a fixed rise. It doesn't matter if you start at the y-axis or start way off somewhere in one of the quadrants. You always should have a fixed rise to go with a fixed run. So for us, our run is 4. The difference between our input values is 4, which means our slope is 3/4. Okay, so this time, again, you can absolutely use point slope form. I have no problems with it, but you don't have to. If you prefer to always use slope intercept form, I tend to use it more often. You can find your b value without using point slope form. So let's just start with the information we have. So far, we know that b of t is equal to 3/4 t plus mystery unknown value of our y-coordinate of our y-intercept. Since I was apparently rude to us and I chose b as the name of my function, I'm just going to call this a big B. It is important that it's not the same variable. If b is your function name, it cannot also be the name of your y-intercept. But a little b and a big B are different variables, so that would be completely acceptable. Another thing you could do, notation that's really common to see in calculus and in some of the sciences, is to use a subscript. Call this little b sub 0 to specify that that is a certain value of function b. In fact, it's the initial value. Okay, so not required, but perfectly legal. To use slope intercept form to find the y-coordinate of your y-intercept, what you would do is take as much information as you've got, which is really just the slope right now, and then you can plug in a single point, any point. What we know is that a point on the graph should make the equation a true statement. It should be a solution to the equation. So by plugging in a known point, I know that the statement I ended up with is a valid one, and I can use it to solve for b. If I just arbitrarily pick an input and an output value and I don't know that it's a point on the graph, I can't assume that this equality actually holds, but that's not what happened. I definitely chose a point that I know is on the graph. Okay, so it looks like I just need to subtract 3/4 from both sides. Notice that 4 is 16/4, which means we're going to get 13/4 equal to b. Excuse me, I almost made it without coughing in your ear. So our equation is b of t, and let me not confuse this, this is a big B, is equal to 3/4 t plus 13/4. Okay, long one, but that was all the examples for function notation to get information for linear functions. Thanks for watching.